So, unfortunately, the provost called an emergency meeting at 2:30 that I have to be in. So, we'll have to finish today around 10 after 2 and have to race back down to the low library, so I apologize. We'll make it up by running over many of the classes. So yesterday when I was talking about the rotations, everybody looked dazed. So I thought maybe it would make sense to go through back to that problem in some detail and make sure everybody is happy. So these are our right-handed rotations. So if we have an X rotation, my thumb goes along X, fingers where the magnetization is, and then I can rotate. For a Y rotation, or a Z rotation, and then these would be the corresponding matrices for X, Y, and Z rotation around the Cartesian axes. And then the problem that we said we wanted to solve, let's see, is this one. So I imagine, so here is X and Z axis, and then Y is coming out of the screen towards me. And just because we have a right-handed coordinate system, it means if my thumb is on Z, X has to rotate towards Y. I can always write the coordinate system in the proper way. Now, we have some resonance offset, so that means that there is, what I wanted to do, that means that there is an offset along Z, right, and then we have the omega-1 field along X, if it's an X-phase pulse. So the effective field is in the XZ plane and is tilted by an angle theta. But for what I'm going to do next, I'm going to instead look at this angle and call this the angle zeta. So obviously the two of them add up to pi over 2. It doesn't really matter which way you think about it, but it'll be a little more convenient to think of it this way. So now we want to know what's the effect of a rotation around omega E, which isn't along any of the Cartesian axes. And what I suggested the other day was doing this stepwise procedure where first I rotate up to the Z axis so that the effective field is along Z, and then I rotate around the Z axis and then rotate back by a minus Y rotation to bring everything back to the original frame. But today, to do something differently from the notes, we'll do first a rotation around Y to bring the effective field to the x-axis, then do the rotation around the x-axis, and then do a minus Y rotation to come back to the original frame. So that would mean that the net rotation is going to be, first of all, a rotation around Y by zeta, then a rotation around X by the angle alpha, which is omega E times the length of the pulse, and then a rotation around Y by minus zeta. A rotation around Y by minus zeta is equivalent to a rotation around minus Y by plus zeta. That never matters to us. We can think of it either way we want. Everybody happy with this scheme? This should, if the Rubik's Cube works, this should do what I want. This should let me do this transformation. And then alpha is going to be something larger than pi over 2. If I wanted on resonance to have a 90-degree pulse, when I go off resonance, omega E is always larger than omega 1. So alpha will always be larger than pi over 2. And again, if I'm near resonance, it won't be a whole lot larger than pi over 2. So my next step, thinking about small rotations, is that I write this as a y rotation by minus zeta, an x rotation by something alpha times an x rotation by pi over 2, and then the y rotation by zeta. So I've just written alpha is pi over 2 plus epsilon. And that would be equal to omega e times the length of the pulse. And the pulse is what I need to have a 90-degree pulse on resonance. And now I'm going to play a game that we'll do over and over again. And the first game is, can I get a new screen? I've forgotten. Oh, there we go. Well, that's not what I wanted to have happen. Okay, so now I'm going to play a game I play all the time, and we'll see, we'll do this with the quantum mechanics as well. So now I'm going to say that R is Ry minus zeta, and then we have Rx alpha, and then give myself some more room. Rx pi over 2, Ry zeta, and then I'm putting on this side Rx to the minus 1 pi over 2, Rx pi over 2, where Rx to the minus 1 is the inverse rotation by 90 degrees, which will be the same as a pi over 2 rotation around minus x, or a pi over 2 rotation, or a minus pi over 2 rotation around x. They're all identical. It just says if I rotate by 90 degrees around x and then rotate back by minus 90 degrees, I haven't done anything. So this is the identity operation. So I can always put the identity operation in anywhere I want. Some operation times its inverse is the same as doing nothing. So that does nothing. But I want to focus then on that sandwich. What does it mean to do a 90-degree rotation by minus pi over 2, a y rotation by zeta, and then a 90-degree rotation by x? And to do that, one way of doing it is now to go back to the slides, hopefully. And here, then, I can write down what the matrices are, and multiply the three matrices together and see what the answer is. So here, for example, if I have a pi over 2 pulse, this becomes 1, 0, 0, 0, 0, minus 1, 0, 1, 0. Right? Would be what the 90-degree x pulse is, because cosine of 90 degrees is 0, and sine of 90 degrees is 1. So with that, if I can remember that long enough, so then we want to multiply we have 1, 0, 0, 0, 0, 0, minus 1, 1, 0. And then the y rotation would be cosine zeta, 0, sine zeta, and 0, 1, 0, minus sine zeta, 0, cosine zeta, and then the inverse, interesting down there, of this would be 1, 0, 0, 0, 0, 1, 0, minus 1, 0. So that these two matrices, this one times this one, have to be the unity matrix, and we multiply them together. And that would be the same as back in the full expression for x, putting in minus pi over 2 rather than plus pi over 2. So now I just have to multiply these three matrices together by the rules of matrix arithmetic. And when I do that, what I get is cosine zeta, sine zeta 0, this one's a minus, sine zeta, cosine zeta, 0, 0, 0, 1. And then we have to figure out what that matrix is. And in many cases, that's not going to be so easy to do. But in this particular case, it is. So cosine, cosine 1 on the diagonal, minus sine and sine. And if we go back to the slides, here we have cosine, cosine 1, minus sine, sine. So our answer was that those three rotations together are the same as a z rotation by the angle zeta. Because the result of multiplying the three matrices together was identical to the z rotation matrix. So this is just our z of zeta. So that means the result of my first the result of my first calculation is then that R is Ry minus zeta Rx epsilon Rz zeta Rx pi over 2. So we replace the three matrices by just the result Rz. And so far everything we've done has been exact. We haven't made any approximations. Now I'm going to make the approximation that we're only a little bit off resonance, so that the zeta and epsilon are small rotations. So if those are small angles, then the rotations commute with each other. And I'm going to move this one over to here, and this one over to here. So I end up then with Rz zeta Rx of epsilon Ry of minus zeta Rx of pi over 2. And now you can probably tell I'm going to play the same game. Now I'm going to put in here Rx pi over 2 Rx to the minus 1 pi over 2. Again, the identity operation. And notice I put these in a different order because I wanted to make another triple where I have a positive rotation, something in the middle, and then the inverse rotation. So this triple says I want to do a rotation around by minus pi over 2 around the minus, with acting on a minus y rotation. So I'm doing two things backwards. Again, I can write down the matrices and multiply the three matrices together, but it's probably obvious if you think about it, that if I rotate backwards, something that's already rotating backwards, that's going to be the same as rotating forwards. But if you don't believe me, you can write down the matrices. And I'll just contend then that these three, Rx to the minus 1 pi over 2, Ry minus zeta, Rx pi over 2, is also a z rotation by zeta. So that then we end up with the final result that R was Rz of zeta, Rx of epsilon, Rx pi over 2, Rz of zeta, and then I can just combine epsilon and pi over 2 again to get Rz zeta, Rx alpha, Rz of zeta, to be the effect of a 90-degree rotation on resonance, what the effect is if we're off resonance by a little bit. And this is basically where I kind of went through quickly yesterday. And our final problem then would be to figure out if we have this angle zeta, what is it in terms of omega 1 and the resonance offset. And then we did that by trigonometry so that we could express zeta in terms of things that we knew, like the resonance offset and the length of the pulse. And that's the kind of thing that comes up pretty often. So if we do that explicitly as well, but here we have zeta, and by trigonometry, tan zeta has to be omega over capital Omega over omega 1, because tangent is the opposite length of the triangle over the adjacent length of the triangle. And then tan zeta is equal to sine zeta over cosine zeta. And if zeta is small, sine zeta is the same as zeta, and cosine zeta goes to unity. So that this is approximately equal to zeta if zeta is small. So a first order Taylor series expansion says that. So then zeta is approximately capital Omega over omega 1. But remember, on resonance, pi over 2 would be equal to omega 1 times the length of the pulse. Since on resonance, we wanted a 90-degree pulse. So omega 1 is pi over 2 over the length of the pulse. So if I substitute that in here, I get 2 omega tau p over pi. And this is equal to omega, let's say, tau hat, where tau hat is 2 tau p over pi. So the pulse can be represented as, so the real pulse, we turn on the RF field for a time period tau p and then turn it off again. But from the standpoint of evolution of magnetization, what we just said is that the evolution looks like we had a little short delay whose length was 2 tau p over pi, and then a delta function, 90-degree rotation, or alpha, rotation by alpha, off resonance, and then another little delay of length 2 tau p over pi. So the physical turn on the off resonance field for a length tau p can be replaced by a delay of length tau hat, a delta function rotation by the angle, an instantaneous rotation by the angle alpha, and then another little delay. So if we think about Z magnetization, what's going to happen? So if I was doing this to Z magnetization, I start with Z magnetization, and now I have a little delay, tau hat, but nothing happens to Z magnetization during a little time delay, right? Because magnetization processes around the Z field, nothing happens. Then I have the rotation by alpha. So if I start with m naught, after that, I'll have m naught cosine alpha on the z-axis and m naught sine alpha on the minus y-axis. And now I have evolution with the frequency capital omega for this delay tau hat. Nothing happens to the Z magnetization, right? It's on the z-axis. So I have m naught cosine alpha z-axis minus m naught sine alpha on the y-axis, and then minus y rotation, minus y magnetization rotates around z and starts to come back to the plus x-axis. X, y, minus x, minus y back to x. So then we'll have plus m naught what did I just do here? Oh, so this should be then cosine omega tau hat, and then we'll have sine alpha sine omega tau hat on the x-axis. So if we look down from the top, here's x and y. If we had a non-resonance pulse, after the pulse, the magnetization just points here along the minus y-axis. But off resonance, the magnetization has started to rotate. So it points here. It's rotated by this angle, omega tau hat. And that's what you would see in the spectrum as a first order phase error. And if you were now acquiring the signal, you probably wouldn't worry about this. You would just apply a first order phase correction. But if this is part of some multidimensional experiment where now this is followed by some delay and then some other pulse, the result isn't going to be exactly what you think it is. Because if you design if you had some delay and then another pulse and you're thinking the magnetization is going to be on the minus y-axis, it isn't. The effect of your next pulse isn't going to do what you think it is. However, if you have something that is, as we frequently do, for example, one pulse, then a delay, and then another pulse. Now we see that this really looks like a little delay, a delta function, another little delay, the period t, a little delay, a delta function, and another little period, where each of these little periods, right, is tau hat. And I thought I wanted to set t here to some value. It was important for me for the design of the pulse sequence, but that's not correct, because from the standpoint of the spins, this really looks like a time period 2 tau hat plus t, because of this effective rotation during the pulse. So I should really, in the experiment, compensate for this by setting this to be tau prime, or t prime, right, where t prime is the value of t I really want, minus 2 tau hat, to account for this little bit of evolution here and the little bit of evolution there. And then I correct the phase problem that I would otherwise have. Now, the problem that comes up there is I might have been setting t to get something to happen with respect to, say, a dipole coupling or a scalar coupling. And now I will have misset t prime a little bit, unless I go back and figure out what happens to the scalar couplings during the pulse. However, in solution, the scalar couplings tend to be pretty small, and that means that this correction for shift evolution can be done in a very short time compared to the length of times that we need for the scalar couplings to evolve. So usually we can ignore that. We can correct for the phase evolution due to the chemical shift by defining t prime and not worry about the j couplings. It's only for really careful cases that we need to worry about that. So in fact, if you look inside of pulse sequences, particularly solution pulse sequences, you'll see over and over again that there are little delays subtracted off to compensate for this kind of effect. So then, what's the result? We have this phase evolution that we can correct for as long as there's a time delay coming next. And also there's a slight reduction in amplitude because we end up with transverse magnetization proportional to sine alpha. And if alpha isn't pi over 2, we're going to have a little less magnetization in the transverse plane. But that's usually not a major problem. Again, out to omega, capital omega over omega 1 equal to 1, the fall off in amplitude is relatively small. In lots of experiments, we might have something that looks like this, where we have a 90-degree pulse, some delay, a 180-degree pulse, some other delay, and then a 90-degree pulse. And then the question is, should we adjust for evolution during the pulse? So again, this really looks like a little delay, a delta function, a little delay, whatever's happening during the 180-degree pulse. So ignore that for the time being. And again, a little delay, a delta function, a little delay. Should we adjust for evolution during these little delays? And now the answer turns out to be no. Because as we saw the other day, the spin echo refocuses the chemical shifts. So if the shifts are evolving, say, looking like they're evolving with the frequency plus omega during this little delay, after the 180-degree pulse, they'll look like they're evolving with the frequency minus omega, and they'll end up canceling. So in that case, we won't correct for the evolution. So one has to pay attention to this, and sometimes it can be a little tricky because now if we had a second 180 inside of this period in between the 180s, then the two 180s undo the effect of each other, and then we have to shorten the delays again, then we have to take things into account. So sometimes it's a little tricky to figure out what you should do. And anyway, so we did that problem in great detail, I hope, that you could follow, because these are the kinds of calculations and manipulations that we'll do over and over again, even when we're talking about quantum mechanics. There, instead of thinking about inserting products of matrices that are equal to the identity matrix, we'll end up inserting operators whose product is the identity operator. So we'll be doing the same kind of thing, just with operators rather than matrices. So I wanted to make sure that you're very comfortable with this problem, this analysis, before we go on. So questions about this? You all happy? Okay. So this is where I left off yesterday, because I didn't want to get started on this. So we left off by just telling you that there were particular operators that were called Hermitian, and they would have the special property that their eigenvalues would be real, And just to remind us, did I actually write that anywhere? I didn't really write it. So what I mean is that if we have some operator, and I'll try to write operators with little hats on top of them, so that you know that they're an operator or a matrix rather than a number, acting on some function, say f of x. If this is equal to a number times f of x again, we say that f of x is the eigenfunction of the operator A, and lambda is the eigenvalue associated with that. So what I just wrote is called an eigenvalue equation. A is an operator, f of x is the eigenfunction, and lambda is the eigenvalue. So Hermitian operators have the will turn out to be very convenient property that they're what's called orthonormal. So that if we have two different eigenfunctions of some operator, and we multiply them together, taking the complex conjugate of one of them, and then integrate, we either get 0 and 1 or 1. We get 0 if the two eigenfunctions are different from each other, and we get 1 if they're the same and they're normalized. More generally, we might get some number times the Kronecker delta if we didn't normalize the wave functions. And this is always true for Hermitian operators. Sometimes, if you were to solve a problem, the eigenfunctions might not come out being orthonormal to each other, but then there's a process called Gram-Schmidt orthogonalization that makes them orthogonal. So it can always be done, but that's just kind of a detail we won't care about. So this turns out to be a really powerful property for us. And in addition, there's a theorem that says that the eigenfunctions form a complete set. And that means if we solve the eigenvalue problem for some operator over some range of allowed values for the parameter x in this case, although there may be more than one variable, we have some allowed range of parameters and we solve the eigenvalue problem and we have a set of eigenfunctions, then completeness means that any function that can be defined in that same space of variables can be written as a linear combination of the eigenfunctions times some constant. And that's really terrific. If we know the eigenfunctions, we can always then reproduce any unknown function as a linear combination of those that we already know. Now the constants might be complex numbers that might depend on time, but they don't depend on x. So here's a picture. Before we do more mathematics, here's just a picture. So what is shown in green is a cubic polynomial defined over the range x goes from 0 to 1. So I just made up a function. So I just took a cubic polynomial, and it turns out that for a function defined over 0 to 1, that starts at 0 and ends at 0. So the value of the function is 0 when x is 0 and is 0 when x is equal to 1. That a complete set of functions are just the sinusoids, in which the different functions are defined by an integer n. So our statement would be that if we add together enough sinusoids where n goes 1, 2, 3, 4, whatever, eventually I can reproduce the blue curve even though there's no sines or cosines here. And when n equals 1, right, the function is the red line, it's just half of the sine function. When n equals 2, I have one cycle of a sine function. And it's perhaps not obvious that I'm going to get anywhere, right? My function, the blue function, is positive everywhere. And I'm saying I can somehow add in that negative function and get someplace. Well, over here, I've just done the best job I can of reproducing the blue curve just using n equal 1, which just gives me sine pi times x. And I'm allowed to multiply by some coefficient to make that agreement as good as possible. So I have some way of finding the coefficients. That's not important right yet. You can imagine I just did it by trial and error. So that's the best job I can do with just that first sine function. And of course, you can see I can't possibly reproduce the offset because the sine is just going to be centered. But now, I add in the next one. I have n equal 2. I add the two together. I have some way of figuring out what the best linear coefficients are. And now you can see things aren't looking so bad. I managed to reproduce pretty well. And over here, now I've taken n equals 1, n equals 2, n equals 3, n equals 4, n equals 5. So I have more and more cycles of the sine wave. And I weight them together, and now you can see things are looking pretty good. I can start to reproduce this arbitrary function as a linear combination of my basis functions. In this case, my base set of basis function is infinite because n can go to any integer. And you might imagine if I do this for dozens or hundreds of terms in the sum, I might start to get quite accurate. And you can see a nice thing that happens here. It wasn't guaranteed, but you can see my coefficients keep getting smaller and smaller and smaller. So in this particular case, the higher frequency terms become less and less important, which suggests there's probably a point at which I can truncate the expansion and say I have a pretty good approximation. That's not always the case. It could be that the very large values would be important. I was just kind of lucky in this case. So there's no guarantee that convergence is fast. So how would I find, so this was just to give you a sense of maybe this is possible. And in mathematics, what I just did would be called a Fourier series, approximating a function by a Fourier series, in this case a Fourier sine series. And I've approximated just a simple function of one variable, x. If my function didn't start and end at 0, I might then need to add in cosines, right? Because cosine would be 1 at the two edges of the box. So now if I add in a mixture of sines and cosines, I might be able to do something more general. But for my simple case, I didn't want to do that. But eventually, we're going to want to approximate very complicated functions by this kind of expansion. And we'll see examples of that. But we need some way of finding these coefficients. And that's where the orthogonality comes in. Because now we'll play this game, this particular game, over and over again. So here, I've written my unknown function as a linear combination of my known functions. And the gain is to pre-multiply by one of the other functions, perhaps the kth one. And I pre-multiply on both sides. And of course, the product of the sum is the sum of the products. So I can move this inside the summation. And now I integrate both sides of the equation. And integration is just addition. When you first learned to integrate, you learned about Simpson's rule, where you divide the function up into a bunch of little rectangles and add up all the rectangles. So integration is just addition, and addition commutes with addition. So I can move the integral sign inside the summation. And now I have the integral of the product, and actually here I've made a mistake. But now I can fix it because of, I really should have multiplied by the complex conjugate on both sides, just in case my function is complex. And now I can use the fact that the eigenvalues, or the eigenfunctions, are orthogonal. The result of that integral is either 0 or 1. It's 0 whenever k and n are different from each other, and it's 1 when k and n are identical. And that means that the summation collapses to a single term. All the terms in the sum are 0 except for the term when j and k are equal to each other. So I pick out only one coefficient, the kth one. So I have a recipe for finding the kth coefficient. So I just have to do this over and over again. I make k equal to 1, I find the first coefficient. I make k equal to 2, I find the second coefficient. And I just do that until I have enough coefficients to approximate the function to high enough accuracy. I might not like doing this by hand. If I need 1,000 coefficients, I'm not going to want to do this by hand, but obviously a computer gets tired much more slowly than I get tired. And if we're clever, we might be able to find functions where we only need a couple of terms to understand what's happening. And we might not need 1,000 terms. And if we have more than one dimension, we just have to generalize so all our integrals become multi-dimensional integrals rather than one-dimensional integrals. There's nothing else special. So is that okay? Really fantastic property. So we've done the example. And I'm going to get bored very quickly with remembering the complex conjugates and remembering to write all the integral signs. So then we'll adopt the notation due to Dirac, which is called Dirac notation, in which we'll introduce this symbol of bracket, some function, a vertical bar, another function, another bracket. And this means integrate the complex conjugate of the first function multiplied by the second function. And in the notation where these functions have indices, like the sine function with the index equal to n, frequently we won't even write the function. We'll just write the indices inside the brackets to make life simple. So that then I could write this function, the function that I'm trying to approximate, to be the sum of expansion coefficients times my eigenfunction, which I'll also frequently call the basis functions. And I've just indicated them by the index rather than writing psi over and over again. So I interpret this to mean the basis function or the eigenfunction identified by some index n. And it could be, in some cases, I need more than one index. to identify them. That doesn't bother me. I'll just put them in there separated by commas. So that then, the way I find the nth expansion coefficient is to integrate the nth function times my unknown function. And that gives me this. And then this is the integral that's orthonormal and collapses to the delta function, so I just pick out this coefficient. So the nth coefficient is given just by this expression where I've hidden all the dirty work. I've hidden away the integral, so it looks much simpler. And this kind of term, where I have the bracket, the function, the bar, another function, a bracket, was called by Dirac the bracket. And then you'll see that we can take them apart. So here I just have the vertical bar, the function, and the other angled bracket. And Dirac called that the ket, because this was the bracket. So half of it, the right-hand part, is just called the ket. And the other half, if I wrote this way, this we will understand to mean the complex conjugate when we write things backwards. And Dirac called that the bra. So the bra times the ket is the bracket. It means the integral. When we take them apart, the bra just means the complex conjugate of the function. The ket just means the function itself. We don't have the integral until we put them together. Once we stick a bra and a ket together, we then have the integral of the first function's complex conjugate times the second function. So this turns out to be an incredibly helpful notation because it hides a lot of the arduous work inside the notation. So then we can do some fancy things. So here, for example, was our definition of what I call the expectation function. The expectation function of some operator was that we took the complex conjugate of a function, multiplied it by the operator. That operator acted on some other function, and then we integrated. And now in our bra-ket notation, we would have the bra of the function side, then the operator, and then the ket. Is that okay? And now if I substitute in for, if I said that, for example, psi, the ket psi, was equal to the sum of some coefficients times the basis kets, and the bra would be equal to the sum of the complex conjugate of the coefficients and the bra of the basis functions, the complex conjugates. If I substitute in, I then have a double summation. I have to keep the two indices separately. Oh, I should put an M here. So I have a double summation over M and N. And now I have this bra-ket sandwiching the operator. And remember, this is the result of an integral. This bra-a-ket n is the result of doing some integral. The result of doing an integral is always a number. It's a number that has two indices associated with it, m and n. So it's convenient to think of that as defining some matrix. Right? If we have a matrix full of numbers, we locate those numbers by giving the row and the column of each number in the matrix. So a matrix is a set of numbers with two indices. So here I could imagine that this number refers to one particular element out of a matrix, in which the matrix rows are defined by m and columns are defined by n. And what about this thing? Here I have two numbers multiplied together, one of which is indexed by m, the other of which is indexed by n. You can see I reversed the order maybe. You thought maybe I should have done mn. I reversed it for my own purposes because I could imagine that that product represents a single number with two indices, the index n and the index m. So it refers to a matrix where the rows are n and the columns are n. So I have two matrices. One I'm going to think of as rows are n's, columns are m's, and the other one, the rows are m's and the columns are m's. Trying to keep the ordering straight. And then just making up the symbols, I could imagine that my product of the c's here came as a result of some other integral. I don't know what that integral is. I'll make up a symbol for it. That it came from this operation, where I had some operator p that I haven't defined, and the result of that operation would be c sub n, c sub m star. So I've just made this up. And later on we'll see if making up these symbols are helpful. But once I've done that, I can replace the c's with p and m. That's just my matrix now that I invented. And I do this because you might notice, or might remember, perhaps you remember, that the sum of over, which one? Sum over m of p and m, a and n, would be the definition of the matrix product. So that's the same then as summing just over n, the nn elements of the product of two matrices, or in this case, two operators, by the definition of matrix arithmetic. And this says we sum up the diagonal elements of the result of this calculation. And the sum of the diagonal elements is called the trace in mathematics. So using the Dirac notation, we come to the conclusion that the expectation value is the trace of the product of this new operator, p, times the operator a. Where the operator p has the definition that its bra p cat generates cn cm star, the elements of a matrix that have these expansion coefficients in them. So p has the feature that it depends on what basis functions we chose. P is going to look different if I pick basis functions that were sines than if I pick basis functions that were cosines or sums of sines and cosines. So this will depend on what basis I pick. But that's a mathematical convenience. What I measure in the lab can't depend on what basis functions I chose. So that means when I want to do the calculation, I can pick a set of basis functions that make my life as easy as possible. And we'll do that over and over again. We might as well use basis functions that are easy for us to calculate for some particular problem if we can figure out what those were. sometimes we don't have any idea what the easy basis functions are. But this also suggests something that we'll do over and over again, is invent some symbols and then hope that we can work out the properties of the symbols and have those turn out to be useful to us. So in this particular case, we've invented a symbol P, an operator P, that turns out to be useful because it lets us simplify this calculation of the expectation value down to just being a trace of some product of things. So P is called the projection operator or density operator. And one reason this is convenient is, and this will probably be the last thing we do today because it's so powerful, I'll give you a week to think about it, is remember the expectation value for in quantum mechanics means we take an ensemble of identically prepared systems, make the measurement on each system, and then average them. But that's not how NMR works. NMR, we have 10 to the 17 spins, and they're in Boltzmann equilibrium with each other. So we have to do something about the fact we have Boltzmann thermal equilibrium in our experiments. We're not doing molecular beam experiments in high vacuum that one might do in a physics department. So we can imagine mentally that our NMR sample is divided into a large number of little cubes, such that each cube is a system that has a bunch of obviously a bunch of particles in it. But each cube, mentally, we can imagine that we could do the quantum mechanical ensemble average for that little cube. And it's at some temperature. And then the next, or in equilibrium, one of the Boltzmann equilibrium states at some temperature. And then the next little cube over is a different element out of Boltzmann equilibrium at that temperature. And we can do the quantum mechanics on it. But those answers won't be the same because they reflect a different part of the Boltzmann phase space. But we can divide the 10 to the 17 spins up into then billions of these small ensembles. And we imagine mentally in every ensemble, we could do the quantum mechanical ensemble averaging. And then we average over the billions of little cubes that are in Boltzmann equilibrium to get the real result. So we have this mental picture of sub-ensembles where we can do the quantum mechanical calculation. Each of those sub-ensembles will give a slightly different result, such that the average over all of the sub-ensembles reflects Boltzmann equilibrium. So it's a little bit of mental gymnastics. And then we don't want to count up billions and billions of little ensembles, because many of them will turn out to be nearly identical to each other. We say we just have to average over the probability that some sub-ensemble reflected some piece of the Boltzmann distribution. And so instead of counting up 1,000 identical ensembles, we could say, well, we have some sub-ensemble and has a probability of 1,000 over n. N is the total number of ensembles. And weight by the probability rather than adding up each individual one. And that argument leads to this equation. That argument says if we average over a Boltzmann distribution, which I'll show for a while by putting an over bar here, we have a second set of integrals to do. We have our integral here in the Rocket notation to get the expectation value for a given subensemble, and then we have to average over the probability, integrate over the probability that that subensemble existed in our Boltzmann distribution of subensembles. I've just rationalized that to you. I can't prove that that was the right thing to do. I just told you a story about it. And in fact, there are deep issues in statistical physics associated with doing this, none of which we care about, because at the end of the day we can say, does this describe the NMR experiment? Because we can go run the NMR experiment and see if it agrees with the theory, and it will to very high precision, and that's good enough for us, even if the statistical physicists want to keep arguing. And then we're just going to play our same game. We're going to substitute in the expansion as the summation, work our way through all of this, and end up with the averaging over the Boltzmann ensemble means, actually this is a mistake, something, oh, I'm sorry, you can see it, I can't see it. When we work through all of this, we then discover that the averaging of the probability distribution means we just have to average over the expansion coefficients. The operator A and the basis functions don't know anything about the Boltzmann equilibrium. They're the quantum mechanical part. What's different are these coefficients, and then we'll define from this projection operator the thermally average, the Boltzmann average density operator with this overbar. And then I'll invent some new symbol because, again, the basis functions don't care about the averaging. The averaging is somehow on this operator P, and I'll call that sigma. So sigma is the thermally average projection operator. It's what we call the density operator. It has these elements of its matrix as well, given by this expression. And now when I substitute in, I end up saying that the thermally average expectation value I'll actually measure in an NMR experiment is the trace of the density operator multiplied by A. And trace, by the way, is commutative, so it doesn't matter which way I write it. You'll see it written both ways. So now I have a very compact result that says, if I knew the operator A for my NMR experiment, so I can go ask my physics buddies, I want to detect the NMR signal, what's the operator A given by, and they will tell me, and we'll see that in the next class. If I had some way of figuring out what the density operator was, and it will generally be time dependent, although I didn't show it here. If I know how to figure out what sigma is, I have a recipe for calculating the NMR signal, the thermally averaged NMR signal. So that's a very, very powerful result. Our next class will be then, how do we calculate the density operator? We've reduced the problem, in some ways we've reduced the problem. But the important thing is that we can figure out how to calculate the thermally average projection operator, the density operator. Then we've taken care of the Boltzmann equilibrium averaging once and for all. We don't have to worry about it and be constantly thinking, how do I average over 10 to the 17th particles? Once we figure out how to calculate the density operator, the Boltzmann averaging is done. And what seems to be a really, really complicated problem turns out to be not so complicated, as long as you're not a statistical physicist arguing over whether the story I told you is true. So we'll stop there because you should go back through this section really on pencil and paper yourself and really make sure you understand the steps, because that also then underlies the kind of mathematics that we'll be doing endlessly for the rest of the course. So if you came in late, the provost summoned me to a meeting, so I apologize. I have to now jump into a cab and hope I can get back to Low Library by 2:30. Or I may not be here next time for lecture. I'll be fired. And so next week we'll do the problems. Well, on Thursday,